Hello students, welcome back to our science video. For today, our topic is the quantum mechanical model. At the end of this lesson, students are expected to explain how the quantum mechanical model of the atom describes the energies and positions of the electrons. Austrian physicist Erwin Schrodinger was a noted theoretical physicist and scholar who came up with a groundbreaking wave equation for electron movements. Based on the experiment conducted by Erwin Schrodinger, assuming that matter, specifically the electrons, could be regarded as both particle and waves. In 1926, he formulated a wave equation that accurately calculated the energy levels of electrons in atoms. It is called the orbitals. Atomic orbitals are the regions in space of an atom where an electron is most likely located. A quantum number is a value that is used when describing the energy levels available to atoms and molecules. An electron in an atom or ion has 4 quantum numbers to describe its state and yield solutions to the Schrodinger wave equation for the hydrogen atom. The 4 quantum numbers are principal, angular, magnetic quantum, and magnetic spin. The principal quantum number, n, describes the energy of an electron and the most probable distance of the electron from the nucleus. In other words, it refers to the size of the orbital and the energy level an electron is placed in. By looking at the periodic table of elements, we can identify the principal quantum number. First, find the element that you want to know the quantum number, then find the principal number, which denotes the element's energy, by looking in which period the element is found. For example, sodium is in the 3rd period of the table, so its principal quantum number is 3. There are 4 types of orbitals that you should be familiar with: S, P, D, and F, or sharp, principal, diffuse, and fundamental. Within each shell of an atom, there are some combinations of orbitals. An s orbital is spherically symmetric around the nucleus of the atom, like a hollow ball made of rather floppy material with the nucleus at its center. As the energy levels increase, the electrons are located further from the nucleus, so the orbitals get bigger. The order of size is 1s to 2s to 3s. For the p orbitals or principal, not all electrons inhabit s orbitals. At the first energy level, the only orbital available to electrons is the 1s orbital. However, at the second level, there are also orbitals called 2p orbitals in addition to the 2s orbital. Unlike an s orbital, a p orbital points in a particular direction. At any one energy level, we have 3 absolutely equivalent p orbitals pointing mutually at right angles to each other. These are arbitrarily given the symbols px, py, and pz. This is simply for convenience, because what you might think of as the x, y, or z direction changes constantly as the atom tumbles in space. The p orbitals at the second energy level are called 2px, 2py, and 2pz. There are similar orbitals at subsequent levels: 3px, 3py, 3pz, 4px, 4py, 4pc, and so on. All levels except the first have p orbitals. In addition to s and p orbitals, there are 2 other sets of orbitals which become available for electrons to inhabit at higher energy levels. At the 3rd level, there is a set of 5d orbitals with complicated shapes and names, as well as the 3s and 3p orbitals. At the 3rd level, there are a total of 9 orbitals altogether. The 5 3d orbitals are called 3dxy, 3dxz, 3dyz, 3dx to the second 2y to the second, and 3dz to the second. The d orbitals are what give transition metals their special properties. In transition metal ions in the outermost d orbitals are incompletely filled with electrons, so they can easily give and take electrons. At the 4th and higher levels, there are 7 f orbitals in addition to the 4s, 4p, and 4d orbitals. Counting the 4s, 4p, p and for the orbitals, this makes a total of 16 orbitals in the fourth level. They have even more complicated shapes. S, P, D, and F orbitals are available at all higher energy levels as well. Fortunately, you will probably not have to memorize the shapes of the F orbitals. Just remember that there are 7 F orbitals in each level from level 4 and onwards. Remember that the shape of the orbitals does not represent accurately in reality. They are just the result of the mathematical computation based on Schrodinger's equation. Therefore, if the electron is found in the first energy level, n is equals to 1. If the electron is found in the fourth energy level, n is equals to 4. This illustration shows the increasing number of electrons from the first energy level going to the fourth energy level. While this illustration shows the different combinations of orbitals in each energy level. If the electrons occupies the first energy level, it has the representation of n is equals to 1. The angular or azimuthal quantum number is a quantum number for an atomic orbital that determines its orbital angular momentum and describes the shape of the orbital. The shape of the orbital depends on the value of n. Look at the table to see the possible values of L from the value of n. If the electrons occupies the first energy level, it has the representation n is equals to 1 and L is equals to 0, since in the first energy level, only the S sublevel is present. The magnetic quantum number describes the energy levels available within a subshell and yields the projection of the orbital angular momentum along a specified axis. The magnetic quantum number specifies the orientation in space of an orbital of a given energy, or n, and shape, or L. This number divides the subshell into individual orbitals which hold the electrons. There are 2 L plus 1 orbitals in each subshell. Thus, the S subshell has only 1 orbital, the P subshell has 3 orbitals, the D subshell has 5 orbitals, and the F subshell has 7 orbitals. Lastly, the spin quantum number or M of S describes the angular momentum of an electron. An electron spins around an axis and has both angular momentum and orbital angular momentum. Because angular momentum is a vector quantity, the spin quantum number or S has both a magnitude, 1/2, and the direction of positive or negative. This is what we do in order to identify the spin of an electron, or simply known as the Oppo principle. To summarize, principal quantum number is represented by letter n, with values of positive integers that refers to the orbital size and energy level. The angular or azimuthal quantum number is represented by letter L, with value of integers from 0 to n minus 1. That refers to the orbital shape of sublevels or subshells. The magnetic quantum number is represented by M of L, with value of integers from -1 to +1 that refers to the orbital orientation. Lastly, the spin quantum number is represented by M of S, with allowed values of +1/2 or -1/2 that refers to the electron spin or direction. Thank you for watching. Do not forget to subscribe for more science and educational videos by clicking the notification bell.